respiration physiology. We're talking about hemoglobin, its ability to transport oxygen throughout the blood. So we first started off talking about these terms known as affinity, which is the desire for binding. High affinity means you have a high desire for binding, but at the same time it also means you're not going to want to let go of it. A low affinity for binding means not a very strong desire for binding, which means though you're going to be harder to pick it up. What would influence hemoglobin's desire for binding or its level of affinity? Some different environmental factors that we walked through. One was the idea of how much oxygen is around hemoglobin, the environmental amount of oxygen. Well, if this happens to be at the pulmonary capillaries of the lungs, then if I find myself at high levels of oxygen, I will have a high level of affinity. That means I'll probably be very saturated. And when I go to environments that have lower affinity, lower PO2 values, the nice thing is, as PO2 values lower, so does my affinity. And the one you really want to pay attention to is the PO2 of 40, because that's what's on that circular diagram, but it also represents the average normal PO2 of tissues. So when hemoglobin gets to your systemic capillaries, and it finds itself in a PO2 environment, roughly 40, it donates one of its oxygens. That's why we tend to say that it is 75% saturated in a PO2 of 40. And then we can see that would drop lower and lower as the PO2 values would lower. Then we talked about how pH would affect hemoglobin's affinity. You want to keep in mind this graph is kind of thinking about two things. The pH, but it's also the pH for any given PO2 value. And we're making comparisons either between people or within a person as their pH values change. Normal pH is 7.4. If you become more acidic, you would then experience a right shift, which is also known as the Bohr effect. The Bohr effects and right shifts deal with a lowering of the affinity, which kind of makes sense if you think about why you've become acidic. You have more hydrogen ions in solution, probably more acid, which means you're probably converting pyruvates into lactates. Mitochondria, you don't have enough oxygen to use those pyruvates. So we have this little system that says, hey, we can make oxygen come off hemoglobin even easier. And if you are to the left of normal, or purple bluish line of 7.4, that would be a left shift. That means the affinity increases. It's harder for hemoglobin to bind to oxygen. I'm sorry, it's easier, excuse me, it's easier for hemoglobin to bind to oxygen. Within the temperature, again, where we compare you at the orange, which would be roughly 38 degrees Celsius. If you're to the right, you're a right shift. That means you've lowered the affinity. So it's easier to let go of that stuff. And if you are to the right, I'm sorry, to the left of it, excuse me, then you have an increase in affinity. That means it's going to be harder to let go of it. Easier to hook up to it, but it's harder to let go. So that lets us look at then the idea of PO2 values, the idea of pH values, and temperature, how they can all influence hemoglobin's desire for binding, or the opposite, which would be releasing of the oxygen molecules. We then went and talked about mom and fetuses. Again, another hemoglobin saturation curve for mom is represented by the red slope, and that's a normal adult saturation curve. And then we're comparing the fetal curve to mom, and the fetal curve is to the left of mom. So it's an increase in affinity by definition. And that means it has a higher desire for binding. And we looked at that on last Monday, and that's because how would you get fetal hemoglobin to get oxygen from mom's blood if they had the same affinity? It wouldn't work. So I have to have a higher affinity due to the gamma globulin that I have in my blood. And that higher affinity, though, causes a problem. It's easier for me to steal it from mom, but it's going to be harder for me to let go of it at a normal adult PO2 value of 40. Well, it just so happens that since fetal tissues are so mitotically active and going through so much mitosis for cellular growth, that they're using up a lot of oxygen. So their PO2 value is lower than the average adult. They're around an 18 or a 19. And since you've lowered the PO2 value, you'll also lower your affinity. So that exceptionally high affinity in the fetus is also matched by an exceptionally low PO2 environment. Therefore, it'll be easier to let go of its oxygen. Up to that point, does anybody have any questions? Is everybody okay looking at these graphs and seeing what we just said? I don't know, I didn't look at the graph to see if I could do that. So make sure you do that over the weekend, all right? Because we have more graphs to look at tonight, just in honor of Sarah for the heck of it, okay? All right. We know there's three ways, Ariel?
Could you explain the significance of the P50 value again?
So the P50 value was a way for me to compare two people in terms of their hemoglobin's carrying ability. That's our standard. The point at which your hemoglobin is at 50% saturated compared to my hemoglobin at 50% saturation. I simply want to know what would be the PO2 value in your tissues that would allow you to be 50% saturated compared to what the PO2 value would be in my tissues that would let me be 50% saturated. So when we look at mom, for example, and the fetus, if we pick that number, then we realize that fetal hemoglobin is at 50% saturation at about an 18 or 19 PO2 value. Well, that's a lot lower in PO2 than what mom's would be. And so if it's lower, that means it has a higher affinity because it's hanging on to the oxygen with a further decrease in PO2s compared to mom. It's a comparative idea. And that means you can also compare animal to animal, species to species. Did I make it a little clear? Okay.
You keep saying mom, and that's as adult. Does they differ when you become pregnant, or
No, it'll stay the same.
Okay.
Yeah. Really, they shouldn't call it adult. Well, they could, but it's usually, as far as I know, most dads are really never pregnant. It's usually the moms. They label it as adult. Okay. We know there's three ways you can transport carbon dioxide. Memorize these numbers. Do not Google it. Don't go looking for Google to see what numbers Google gives you. Memorize these numbers. Right? 70% of the form by carbon ion. If I already asked you to explain to me why, you'd be able to do that. Because you've already memorized that really fun equation, right? Because we're going to see it again tonight. 23% by a protein. Yeah, it's going to cost you points. You got to say hemoglobin. Because there's all kinds of proteins in your blood. I want you to be specific. So it's simply just easier to say 23% carried by hemoglobin. And then you got 7% dissolved as a gas in plasma. Right? As a gas in plasma. We can see that in this diagram over here, and also lets us realize there are only two ways that we transport oxygen. 3% dissolved in plasma, and the rest of it is hooked up to hemoglobin. That would be roughly 97%. All right, we'll get back to this slide a bit later tonight. All right, now, where is the control center for your breathing? It's a part of your medulla known as the respiratory rhythmicity center. It's a group of autorhythmic cells, like the SA node is, of these paired nuclei are called the DRG and the VRG. From the DRG, you'll get a phrenic nerve that goes to the diaphragm to cause contractions at a rate of roughly 12 to 15 times a minute. That's your normal rhythmicity, your normal breathing pattern, without any external influence. In the pons, we also have a group of paired nuclei known as the pneumotaxic and aponustics. And apparently there's a discussion about really who's in control, so we're going to just default to this set of lecture notes until further evidence supports the claim made by McKinley in his textbook, and that we're going to say that DRG is the controller of your normal natural breathing. And all we're going to look at for the pons is that its job is to influence what the medulla does. to influence your DRG and your DRG until further evidence turns us upside down. All right, so let's look at what would influence maybe the pneumotaxic and apneumotic. What would influence the DRG and VRG? We have to measure the level of dissolved gases in your blood. PCO2, PO2, and hydrogen ions, in other words, your pH. Well, what things would be monitoring the level of dissolved gases in your blood? They're known as chemoreceptors, because those are chemicals. You have two types of these chemoreceptors, one called central and one called peripheral. The central is called central because it's found in the medulla, which is a part of your central nervous system. Now, it does indicate the level of CO2. But this is why it has a nickname of hydrogen ion sensor. It doesn't actually respond to CO2. It responds to hydrogen ions. But it does indicate the level of CO2. That's why it's called the hydrogen ion sensor. The peripheral chemoreceptor, which is found in the aorta and the carotid, does respond to O2, but it's usually significant drops in O2, like maybe a PO2 of 60 or less would trigger you to breathe faster. So it has to be a significant drop in O2. If I were to somehow on page 3 ask you to describe the function of the peripheral chemoreceptors, and you were to say it responds to lower O2 values, I'm not going to give you full credit. Because if normal is 100, you talk about 98, about 90? No, you got to say, right, like in tachycardia, right, a resting heart rate greater than 100. You're talking about PO2 values of 60 or less, right? The devil's in the details. All right, well, let's talk about some other things that would influence, because we're going to come back to the centrals and peripherals a bit later. We also have in the carotid and in the aorta pressure sensors. Remember, baro refers to pressure, like even for cardiac cycles. Well, we also have one for respirations, for baroreceptors, right? Affects blood pressure and respiratory centers. Remember, those respiratory centers would be in the medulla and in the pons. So, how is blood pressure going to do this? When blood pressure falls, respiration bless you, right? Respiration will increase. So a drop in blood pressure makes you breathe faster. Now, once you memorize that, then let logic take you the other way. What is the opposite of that scenario? Well, how about when blood pressure increases instead of falls? All right, and then the opposite of that would be a drop in respiration rates. Because really every time you inhale and exhale, you're actually changing the pressure of the blood vessels in your thoracic cavity. And we want to help maintain a normal blood pressure, so we need to influence your breathing rates. So when blood pressure falls, respiration increases. When blood pressure increases, respiration rates will decrease. All right, so the question is, if you're looking at two different kinds of gases, CO2 and O2, in your blood, we want to talk about which one of those two are you actually more sensitive to. Which one can we experience the smallest change in to get an increase in respiration rates? And a lot of us think, well, duh, it's got to be O2 because that's what keeps us alive. Well, let's see if that's right. Practice in reading Yippee Skippy Graphs. First thing, look at the x-axis. What is the topic on the x-axis? You are looking at arterial PO2 values. All right? We can even imagine a mark here of 130. Now, what's on the y-axis, right? Minute ventilation, in other words, liters per minute, which is respiration rates in a sense. Of these two, x and y, y and x axes, which one is the dependent variable? Oh my goodness. Daniela, do you know? Or should I say student, do you know?
Arterial pressure in
Nope. Remember in graphs, y depends upon the x. So the dependent variable is ventilation rates. Why is that significant? Because what we're saying then is that respiration rates is dependent upon arterial PO2 values. And you can even see that in the graph. Look at the green slope here for a moment. Right? And if we imagine 130 here, from 130 to 120, from 120 to 110 to 100, is there really much of an increase in ventilation rates with a drop of 30? No, right? It's a huge tolerance. At one point, do you actually, on the graph, at what point do you actually begin to see a significant increase in ventilation rates? In which? About 60. Huh. Doesn't that correspond to what I said is the job of peripheral chemoreceptors? Responding to a significant drop in PO2 values of like 60 or less, I said. Right? There's the data proof of that. Right? I'm experiencing significant drops in PO2, but apparently I'm not getting any change in ventilation rates until I got to a PO2 of 60. And then look at the slope. It's a lot steeper. For every notch below 60, I start breathing faster, 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 and faster, trying to maintain that arterial PO2 value. So a part of this that will help you is remember the rule in statistics or in data. Y's are dependent variables. That means whatever the topic is on the y-axis, it depends upon whatever the topic is on the x-axis. And then look at another good trick for graphs. Look at the range of data on the x-axis, right? The data value range. We go from 0 to 130 by increments of 20. Compare that idea to this idea. Look at the x-axis. Do I go from 0 to 130? No, we're going to go to highest 48, right? And are my data points by 20s? Well, they're by 4s. That should tell you that this is a more sensitive bit of data, that we're looking at smaller increments of change. That means we're probably less tolerant because the data points are at smaller intervals. And again, the y depends upon the x. But what's the topic on the y-axis? Ventilation rates. And what's the topic on the x-axis now? CO2, right? Not O2. Is it fair to say that for every increase in PCO2, I'm going to get an increase in ventilation rates? Yeah. Did we have that over here? No, we had a huge tolerance of drops in O2, right? Before we got to this. So apparently we're very sensitive to increases in CO2. Does anybody have an idea as to why we're way more sensitive to increases in CO2 than we would be to drops in PO2? It's going to be your favorite equation. It relates to this. So look at the slope of this graph. Look at the slope for a second. Now look at the slope. Are they roughly the same? No, crudely they are, right? They're both going up pretty quickly compared to this damn thing, right? Where you have a huge horizontal aspect to your data points. But here, right, like a takeoff, and here it's like a lift-off. This is more linear, right? But again, with this one I can say, for every change in x, I get a change in y. Well, what's the topic on the x-axis? You gotta be careful how you read this. Plasma hydrogen ion concentrations. So there's my hydrogen ion concentrations. They're getting larger as I go this way, right? But they impose upon you another scale, the pH scale. And pH isn't getting higher as I go this way. It's getting what? Lower. And lower pHs, does that mean more acidic or more alkaline? More acidic, which makes sense because the more hydrogens you have, the more acidic you will be. So you kind of want to notice what they're doing on the x-axis. So why is it that this is a graph about how pH influences ventilation rates? That the more acidic you become, right, the faster you breathe. The more CO2 you have in the arterial system, right, the faster you breathe. Why is that? Anybody know? What do you mean by bicarbonate?
HCO3.
HCO3, well, it's a buffer. You're in the right ballpark. But right now, you're the LA Dodgers. What are you maybe thinking that I haven't actually quite said just yet? Where did the bicarbonate come from?
CO2.
It came literally from CO2?
CO2 plus hydrogen.
Well, it came from carbonic acid, right? Which came from what? The interaction between water and CO2, right? And that's what I want you guys thinking about. I mean, Derek was really close. CO2 plus H2O is going to give you carbonic acid. But then that will disassociate into a bicarbonate, but that's an alkaline buffer. But there's your hydrogen ions. So I'm hoping you all would break the fan here. Agree that if you had an increase in CO2, that would lead to an increase in hydrogen ions. That's why these two graphs are very similar, right? They're related.
Does that happen when CO2 hits the blood from like tissues?
What's blood mainly comprised of?
Water.
Exactly. All right. Now remember, do you remember I think it was Katie that asked this. Do you remember the name of the enzyme that makes us go a lot faster and more efficiently? Oh, don't look, don't look. Do you know it? Its abbreviation was for a state,
CA.
which stands for carbonic anhydrase, right? That makes us go a lot faster.
So that's just sitting around in the blood.
Yeah, it happens in a glass of water. It happens in your oceans. This is why our oceans are acidifying. So anytime CO2 hits water, you're going to do that. Anytime.
When does it go back?
It goes back and forth. Remember, it's a two-way equation. Right? So stoichiometry, if you had more reactants, you get more product. More product would lead you to more reactants in that sense. So you guys kind of seen how this one and this one are kind of related to each other, right? All right, now, what is the dependent variable on this graph? Boy, I wasn't very good. Jessica, what's the dependent variable on this graph?
Ventilation rate.
Katie, what's the dependent variable on this one?
Ventilation rate.
Daniela, what's the dependent variable on this one? So, ventilation is controlled by PO2. Ventilation controlled by PCO2. Ventilation controlled by pH. What about this one? Holy crap, we just flipped it.
X.
Who's on the y-axis now?
Pressure.
Partial pressure of the alveoli, right? All right, and what's on the x-axis? Oh, now ventilation's on the x. Huh. All right, so how do you read this damn thing? Alveolar or lung partial pressures of what? Of O2 and CO2 apparently are determined by how fast you breathe. Right? And that's the basic opinion of what a graph tells you. All right, well, over here are your ventilation rates, right? 1 to 8 in a minute. Look at the orange slope. Follow the orange data points for a second. Tell it to yourself, what is that graph telling you about oxygen? Or alveolar PO2s? How would you read that graph? And I think I'm going to guess that most of you are going to miss one key way of expressing the idea. And this is what the graph says. As ventilation rates, right, increase, I start to get an increase in alveolar partial pressures of O2. We're all good with that?
Yeah.
Right? The faster I breathe, the more O2 I get, up to a point. And this is going to begin to actually flatten out. So really, at some point, if you try and breathe at 9, 10, 12, 15, 20 liters a minute, you're not going to get anything but dizzy. You're not going to add more O2. This is why I'm kind of fussy about slopes, because it has to communicate an accurate representation. At some point, if you breathe faster, you're not going to get any more O2. It's going to plateau out. And look at this, look what happens correspondingly. If the faster you breathe, the more O2 we can get into the lungs. What happens to CO2? Just the opposite, right? The faster we breathe, the lower the CO2 gets until we also have another plateau. But this is about how ventilation is now controlling partial pressure of gases. It's the complete opposite of the first three. And all you have to know is how to read a graph, and it'll tell you that. Okay, you ready to see how this talks about how ventilation controls O2 and Paula?
Sorry, could you go back to that equation tying into why we are more sensitive to the CO2 changes in CO2?
Well, so does CO2 lead to a decrease in pH?
Increase in pH.
Increase? If you have more hydrogens, does pH go up or pH go down?
Oh,
Yeah.
it goes down. Sorry.
It goes down, right? All right. And enzymes are really fussy about pH. And your blood pH range is 7.35 to 7.45. It's not a very wide range, right? It's a factor of 10 units. So we have to maintain a very narrow range of pH. And since pH is influenced by CO2 values, and O2 doesn't cause a change in pH, so we can be more tolerant to losses in PO2. But there's also one other factor that would dictate as to why, which I wasn't going to get to just yet, but since Paul's question led to it. Do you think of any other possible explanation for why we can tolerate such a long drop in O2? It's a bunch of goofy trivia I had you guys try and memorize. How many hemoglobin molecules per red blood cell? How many hemoglobin molecules per red blood cell? 280 million, right? All right, now, on a single hemoglobin, how many oxygen molecules can you attach? 4. So you got 4 times 280 million, that's in one red blood cell. And roughly how many red blood cells per drop of blood? 260 million, right? And there's roughly 15 drops per milliliter. And then you've got 1,000 milliliters per liter, and you have 5 liters. You have a shitload of oxygen on your hemoglobins. So I can afford to let go of 1, let go of 2. I can even be 50% saturated and still have enough where I don't need to make John breathe faster. We have a huge oxygen carrying capacity. That's why we can tolerate significant losses in O2. But we are limited by our buffering system. pHs we're very sensitive to. And since CO2 leads to changes in pH, and hydrogens lead to changes in pH, we respond very quickly to changes in those for ventilation. Because, let's look at this. What happens to the amount of CO2 in the lungs if I breathe faster? It drops, right? All right, now, if this lowers, that allows the equation to go this way. What's going to happen to the concentration of hydrogens if the equation goes this way? It's going to go down. What happens to your pH in that sense? It goes up. So what if I'm becoming what's known as respiratory acidosis? I have an acidic blood condition. If I breathe faster, can I lower my pH? Yeah, if I breathe faster, I can lower my CO2, right? If I lower the CO2, that allows the reaction by chemistry to go this way. That would increase my pH. If I'm rather alkaline, I can slow my breathing down, let CO2 accumulate, which leads to an increase in hydrogen ions, which lowers my pH. So respirations can help balance out changes in blood pH. Acidosis or alkalosis. I can either breathe faster or I can breathe slower, and that can change the pH of my blood. So I can help maintain a more stable range of values. Does that conversation make sense? I'm just going to keep moving so Celeste has to keep changing the camera. Okay. Oh, shoot. Don't worry, I have a surprise for you.
Can you stop those words that I
got acidosis
Yeah.
and alkalosis.
Yeah.
This means you're acidic or alkaline. No, you want acidic?
Yeah.
It's simply just acidic. Right? And alkaline.
Oh, okay.
No, nothing fancy.
There's an E on the end.
Well, I'm finishing. You stopped though. All right. So we're gonna do this. Take a 6-minute calling break, and then we're gonna come back and we are going to talk about how you can accidentally kill grandma. No, that's intentional. That's not accidental. Anyway, what's your question, Colleen?
So to verify if you are acidosis and
Yes. If you're alkaline, you need to lower your pH.
Unintentional.